Good evening to all. We'll wait 5 more minutes. Only 65 members are joined out of 340 participants. We'll wait 2 more minutes. Like that, we'll start that session. Huh? Okay, we'll start that session. It's already 6:03, right? Okay. So welcome back, everyone. We are now ready to begin session 1 of day 4 of our faculty development program on the revolution of LLMs, large language models in AI. Myself, Dr. Anusha Ampavati, coordinator of this FDP. As we move forward with the day 4 of our FDP program, it's once again my honor to invite our respected HOD sir, Dr. A. Oble sir, to share few words. Thank you. Over to you, Oble sir.
Thank you, madam. Thank you so much. ATAL FDP, Department of AI on LLM models. This is the fourth day. We got very good feedback last 3 days, and continuously every session more than 250 members are joined. Thank you very much, all the participants. Now today also very good 2 sessions are there, more innovative ideas. So please, I request all the participants, without disturbing the presentations, please enrich your skills with the practical knowledge also. So once again, I would like to thank this program coordinator, Dr. Anusha ma'am, and co-coordinator Rambabu Garu. Please, thank you so much for your contribution. Thank you all. All the best. Over
Thank
to
you
you,
so
ma'am.
much. Thank you so much, sir. Thank you so much for your support also. I would like to invite Dr. Uma Maitri madam. Uma Maitri ma'am, I want to give you some general information before giving to the mic to Uma madam. Today we have the 2 sessions, just now Oblesir said. Okay, first one is application of RNNs and LLMs in real world scenarios by honorable guest and speaker by Dr. KV Kadambari Garu. And the second session was, the topic is the influence of NLP and LLMs on addressing healthcare challenges by Dr. Sirisha Velampalli Garu. So now I wanted to give to mic to Ms. Uma Maitri Elisetti to introduce our honorable guest of session 1. Over to you, Uma ma'am.
Thank you, ma'am. Good evening, ladies and gentlemen. I am Uma Maitreyi Elisetti, an assistant professor, Department of Artificial Intelligence, Vidya Jyoti Institute of Technology. It's my honor to introduce our honorable guest, Dr. K.V. Kadambari, ma'am. Dr. K.V. Kadambari, an associate professor in the Department of Computer Science and Engineering at NIT Warangal. She completed her PhD in Computational Neuroscience from JNU, New Delhi in 2011. She holds an MTech in Computer Science and Technology from Andhra University 2004 and a BTech in Computer Science and Technology from PVP Siddhartha Institute of Technology, Vijayawada. Her research interests encompass neuroscience, neuroinformatics, neuroimaging, machine learning, and computer vision. Dr. Kadambari ma'am is recognized for her innovative contributions as evidenced by her co-invention of an accelerating learning method for support vector machines, granted an innovation patent in Australia in 2021. In her extensive list of publications, she has contributed to journals such as Biological Cybernetics, IEEE's Global Engineering Education Conference, ACM's ICBBT, and many more. Dr. Kadambari ma'am has supervised several PhD candidates and remains actively engaged in cutting edge research. She has organized and co coordinated various workshops, conferences, and faculty development programs showcasing her commitments to knowledge dissemination. These include workshops on machine learning, big image data processing, recent trends in graph theory, and social signal processing. Dr. K.V. Kadambari ma'am is a dedicated academician, contributing significantly to both research and education in the field of computer science and engineering. I humbly request Dr. K.V. Kadambari ma'am to take the proceedings of this session. Over to you, Dr. K.V. Kadambari ma'am.
Hello, everyone. I hope my voice is audible to all.
Yes, ma'am, it's audible, ma'am.
In the introduction that you just now gave, the 2-minute introduction, I mean, in my life, I never heard these many times Dr. Kadambari, Dr. Kadambari. I feel that my effort of all these years of studying, doing PhD has been fulfilled today by hearing my name, Dr. K.V. Kadambari, so many times. Yeah. So today, as you just now mentioned, I will be talking about what they call recurrent neural networks first, and then going on talking about other advanced NLP applications, because the title itself talks about large language models, so I wanted to give you the basics of some NLP techniques which are used behind what they call LLMs. So that was my idea. And without any further delay, let me start off. Let me share my screen. So I hope the screen is visible to all.
It's visible.
Yeah. So the first topic of my day is introduction to recurrent neural networks. And this would be my agenda for this lecture, like what is the motivation behind using recurrent neural networks, the architecture of a basic RNN unit, which is called as a vanilla unit because it's a plain RNN. Then go on to discuss RNN feed forward network and different applications. Then what are the advantages and disadvantages of RNN and how they can be overcome by using LSTMs. That means I'll take one example and tell you how LSTMs actually work. Okay, so let's dive into the lecture now. The first is like, why do we require RNNs? That is, what is the motivation behind using RNN? RNN actually falls in a category of models called as sequence models. RNN, it falls in a category of sequence models. That means wherever you have applications related to sequences, like for example, speech recognition, which is a frequency kind of a thing. Then you have time series prediction, what they call in case of machine translation, in case of sentiment analysis, text summarization, all these are nothing but sequences. Okay, one word follows the other, one timestamp follows the other timestamp. So that ways. So all these are applications of sequences in the sense like the data is somewhat in the form of a sequence. Okay. So RNN is mainly used when you have data in the form of a sequence, and hence it's called as a sequence model. And why RNN is used? Because in some applications, you will not be having a fixed length input and a fixed length output. Like for example, if I ask you to predict a word in a sentence, if I ask you to fill in a blank in a sentence, you will have to analyze the entire sentence and then try to fill in the appropriate word, okay, in the blank. So for that purpose, I mean, you're giving the whole word, whole sentence as a input, whole sentence as an input, and then asking it to predict the missing word, right? So you're just going to give one word as the output. So when you have problems of such sort, that is conversion into one fixed length inputs to one set of outputs, you can't do that with using normal artificial neural networks. That is one problem. And then for speech recognition, I mean, who is talking, what you are talking, which language you're talking, what are you intending to say? All these things can't be also done by normal ANNs. And so far, ANNs haven't been able to explore the training over time, in the sense like over a time window. That can't be done using your ANN. So for such kind of disadvantages, to overcome them, we are motivated to use recurrent neural networks. In fact, recurrent neural networks, it overcomes all these kinds of problems that I just now mentioned. Okay, so that's the main motivation behind the popularity of RNN. Now, moving on, let's see the architecture, which comprises of actually 2 points. That means before describing you the architecture, I just want you to focus on these 2 points. The first point says that RNN takes the previous output or hidden states as input. That means RNN actually takes the previous hidden layers, previous units hidden layers output as its concerned input. Fine. And this is done over a time period. This is done over a time period T. Okay. And now the next point is RNNs are useful as their intermediate values are stored. Means the main advantage of using RNN is that it can store information. That means the memory component is added inside the RNN. Okay. Memory in the sense the past inputs are added or stored inside your RNN. Now let's analyze these 2 points using the architecture of RNN. So the first point, as I mentioned, it says that you take the previous output and feed it as the current output input. So let's see. The picture that you're looking here is the picture of the vanilla RNN, or also called as the basic RNN unit. Here T represents the timestamp. And as I mentioned in the beginning of the lecture itself, I said you don't have any neural network which focuses over time period. So RNN does that. Instead of taking iterations or instead of considering epochs, we consider something called as timestamps. Okay. So T here indicates timestamp. And when I say T equal to 1, it basically means we are talking about timestamp 1, and X1 indicates input. X indicates input. Okay. And H here indicates the hidden layer. I mean, X is connected to the hidden layer, right? So X, the value of X goes into H. And from the hidden layer, we go to the output layer, which is indicated by a Y. Okay. So since they are done at timestamp 1, all of them have the subscript as 1, X1, H1, and Y1. Okay. Now moving further, at timestamp 2, if you notice, we have X2 going into H2 and then going into Y2. But apart from this normal usual architecture, we also have added something new, which is the output from H1. The output from H1 is fed as input to H2. Output of H1 is fed as input to H2. Okay, so this is what the first point in the previous slide meant. Output of the hidden layer, previous hidden layer, okay, that is fed as input to the current hidden layer. So apart from X2, okay, H2 will also receive input from H1. That means H2 is receiving 2 inputs. H2 is receiving 2 inputs. One is from H1, other one is from X2. Please remember this architecture, because in LSTM we will be implementing this architecture itself. Okay. Then using these 2 inputs, we will be generating an output by 2. Fine. And the same goes on T equal to 3 and T equal to N. How long ever is your window, time period window. Okay. And for H1, initially we will be taking some random value, which is called as H0. Okay. So this is the basic architecture of your vanilla RNN. Okay. Now, moving further, let's look at how what happened? Yeah. Let's look at how the processing is done. Processing in RNN basically is done using an activation function. You might be already knowing that in any type of neural network, we have different types of activation functions. Some are sigmoid, some functions are sigmoid function, tan H function, ReLU function, softmax function, etc. Correct? So in vanilla RNN cell, we use tan H function, which gives you the output between -1 and +1. Okay. So as I mentioned, if HT is the input, okay, if HT is the unit, then XT and HT -1 will be the inputs for that, which will be fed into the TANH function. And XT always will be having some weight associated with it. And the weight is indicated by W, the variable W. Okay. So this is how the processing happens in case of your RNN cell, each RNN cell. Then coming to the feed forward pass. Okay. If you notice, as I mentioned earlier, at t equal to 1, please look at the cursor. Please notice the cursor. At t equal to 1, x1 is the input, h0 is the input. You feed it into a tan h function. Okay. And then you get an output for h1. Then in h1, again, you do some mathematical processing and get some output as y1. Okay. Similar fashion, the rest of the cells also follow. But one important observation that you need to make here is that from y1 itself, we are calculating individual loss, which is called as C1, C2, so on, CT, basically, general notation for any time stamp. It is called as CT. So your C actually here indicates the loss. That means if you are trying to predict a word in a sentence, then whether that word is the correct word or not, that is indicated by your loss function. Okay. Now, I think someone is drawing on my screen. Anusha ma'am, can you just...
Ma'am, for you only it will get terrace option, ma'am. You are sharing that screen, right? Left side, some tools will be there on it.
No, there is no erase option in my thing. Someone else drew it. So they need to... I think you had given the option of annotation to them.
No, ma'am, we blocked it. Just give me 1 minute time, ma'am. I'll do.
One second, I'm doing it. I erased it. Fine.
For you only it will get, ma'am. I mean, you are sharing the screen, right? So okay.
Okay, no issues. So one thing is like for each RNN cell, we are getting C1, C2, C3 as different losses. But what's the point in getting different losses? Because a sentence, if we have an English sentence, the words are always interrelated with each other, correct? I mean, one word is dependent on the other word and the third word is dependent on the second word. So there is a connection between all the words. But unfortunately, if you notice here, there is no connection between C1, C2, C3 because all the losses are treated individually. So what we are doing in vanilla RNN is adding another component which is called as shared weights. Okay, they are called as shared weights. What it means is that whatever processing is being done in a single RNN cell, that information is also being shared with the rest of the RNN cells. Okay, that is what these solid lines are indicating. So the loss in C1 is shared with loss in C2, and the same is shared with loss in C3. The same goes, whatever output you're getting at Y1, it will be shared with Y2, Y3, etc. Who is this? Some Pankaj Palika something. She has been team.
Ma'am, please don't disturb the speaker.
Sorry. Some participant. It starts with P. Palika or someone. Yeah, Palika Jaju. She has been writing on the screen. Yeah. So coming back to the point, the solid lines that you are observing here, they are nothing but sharing information between all the RNN cells, because when the RNNs are not giving you the correct output, okay, the rest of the RNN cells also need to update their information. They need to update their information. And this is the most important or critical aspect of your deep neural networks, that is sharing of weights. This is how multiple stacks communicate with each other, multiple stacks of hidden layers, multiple stacks of neural networks. They all communicate with each other because of sharing of weights. Weights are nothing but information in a neural network. Okay. And this information plays a very important role. That means this aspect, sharing of weights, it plays a very important role in case of RNN, because in RNN, we are mostly dealing with sequences. So when we talk about sequence, the first beginning, everything we need to keep into reference, keep in mind. Okay, so this advantage actually helps us a lot. Okay, and moving further, the architecture that you are just now seeing, okay, this particular architecture that you are observing here, this is called as unfolding network through time, that is making copies at each time step. I'll give you one example. Like for example, you take for loop. I mean, I don't know how many of you have done C or C++ programming, but these are the basic programming languages which we learned during our BTech or even in BCA, BSc, etc. In that we have an iterative loop called as for loop, in which we write give three conditions on a particular variable. Like for example, if I say for I equal to 0, I less than 10, I plus plus, okay. What usually happens is that the value of I will be changing in each iteration. The value of I will be getting updated in each iteration, but the address of I will remain the same. I mean, only the values will be replaced when I is equal to 1, 0 will be replaced with 1. When I is equal to 2, 1 will be replaced with 2, so on and so forth. The memory cell, okay, will remain the same. The address space will be remaining the same. Only thing that will be changing in that address space is the value of I. Okay, the value of I. So the same logic can be applied to your RNN cell also. RNN cell at a given time stamp, will be holding one random value of X. Okay, will be holding some random value of X. Accordingly, it will be giving you the concerned H value, and from H you would be getting your concerned Y value. Okay, so the this outer box will be the same. The outer box will be the same. So at t equal to 20, this our input will be x equal to 20 and h 19. The output will be h20 here, and the output will be here as y20. So that's what we call as folding. And this architecture is unfolding. It's similar to a Chinese paper fan that we have. Okay. So those are called as unfolding, and unfolding basically happens when we want to expand and we want to study each and every time step, what was happening, what was the output at each time stamp. Okay, so that's what we do. Next, the recurrent neural networks, the main thing is, now that you have known the architecture, the other aspect that you need to remember is it shares weights over time. And the other thing is copies of the RNN cell are made over time. It's called as unrolling or unfolding. Okay. So the at different timestamps we'll be taking different inputs and we'll be getting the different outputs from them. Next, coming to the application part, the applications are actually divided in the form of input-output scenarios. That means, are we giving single input? Are we giving multiple input? That ways. Okay, what would be the output? So if we take a simple architecture, it is single means single input and single output. This is called as your simple feed forward network. Then your other architecture is single input and multiple outputs. An application of this is image captioning. The other architecture is multiple inputs and single output, that is sentiment analysis. Last one is multiple, where you can have applications like machine translation, image captioning, etc. Now let's take some few examples of these. So before talking about examples, like the idea behind these examples is based on the input-output architecture. Your training also will be changed. I mean, the training architecture, the neural architecture also will be changed. Okay. So, for example, at each time step, provide previous word as input for image captioning. So that's where that architecture, what we'll be using is single to multiple or multiple to multiple. So based on the application at hand, your architecture will be defined. Now let's dive into the application part. The first application is sentiment classification. Okay. So the first is classify a restaurant review from Yelp. Okay. That means Yelp is a review platform where you can review a restaurant's this thing, okay, or movie review from IMDb, or given a sentence, you are trying to predict whether it is a positive or a negative sentence. So inputs are multiple words, okay, or one or more sentences, and output will be either positive or negative classification. Let's look at two examples. The first is the food was really good. Okay. So this sentence, if you notice, we need to predict whether it is a positive sentence or a negative sentence. Can any of you please tell if it's a positive or a negative? Is it positive or negative?
Participants, you can unmute yourself.
Positive.
The positive sentiment.
Okay. What about the second sentence? The chicken crossed the road because it was uncooked.
The negative sentiment.
Why? Good for the chicken, no?
Visibility is less, ma'am.
What is less?
Feasibility of the sentence.
Feasibility. What do you mean by feasibility, ma'am?
It's a general approach. With respect to our general knowledge, the sentence is not having some sort of a relation. Information. You could.
Information. Okay.
Mm.
Such sentences are actually called as ambiguous sentences because they have partial information with them. We don't know whether to put them under positive or whether to put them under negative. Like for example, sarcasm also is an example of ambiguity. We can say that, wow, you did a great job by bunking the class. So when I say great job, that basically means it's a positive word, but bunking the class is actually a negative thing. So that's where ambiguity lies, and that's where NLP actually fails. Fails in the sense that's the biggest challenge that NLP has, which is ambiguity. Okay.
Yes, ma'am. Yes.
So yeah. So now moving on further, let's take some examples of how this architecture works for a given sentence. So the thing was like, this is our sentence, the food was really good. Okay. And each architecture is defined like this, RNN, and wahan se H1 aaya, then it goes to RNN again, then from there H2 you got. Last Hn minus 1 went to another RNN and gave some Hn as output, and that from there we try to classify it as positive or negative. Okay. Now, in that given sentence, the food was really good. What words in that sentence made it into a positive sentiment? Which words in that sentence converted that sentence into positive class? The food was really good.
Good. Good, ma'am.
Good. Only good. Okay.
Only good.
Then what about the rest of the words? The food was, etc. Can we ignore them?
Cannot ignore.
Cannot ignore.
Mm.
Can I write the movie was really good? I can, right?
Yes, ma'am.
So these words can be ignored because we want to find out which words actually have a huge impact in case of the positivity. Okay, that's how your NLP works. I mean, language processing or sentiment analysis works. I'll at the end of this lecture, I mean, as we proceed further, I'll tell you how the sentiment analysis and all that stuff is done using BERT name by LSTM and all. Okay. So these words at the moment, the food was really, those can be ignored. Okay. And whatever output we get from each and every RNN cell, that is summed all together. The words which are ignored, those would be having lesser probabilistic value. The ones which have are supposed to be kept or are important in the sentence, they are given higher probabilistic value. And that is the reason why the activation function is tan h +1 and -1. +1 and tan h function, it helps us in giving importance to each and every word in the sentence. That means the weightage. Okay. So using the sum, you would be then deciding whether it is a linear or whether it is a positive or a negative sentence. Okay, now coming to the other application, this one is image captioning. Given an image, produce a sentence describing its contents. Input is image feature, okay, which are generated from CNN. And output obviously would be multiple words, okay. Like for example, here you can see the dog is hiding. That is one application. But usually what happens in case of CNN is that if you use techniques like mobile net, YOLO, etc., they are used for object identification. Object identification, and their probability score is given. So they are used for identifying what objects are present in this image. Once you get the object name, then we convert all the objects into a meaningful sentence, put all the objects into a meaningful sentence. Okay, so that's how this caption is generated. The dog is hiding. So this is the basic architecture. And these are some of the examples. A person riding a motorcycle on a dirt road. That means a person is identified as an object. Motorcycle is identified an object. The brown color behind the road, that is identified as a dusty road. So these are tricky examples, but then our CNNs are advanced enough to identify what is happening. Even videos are also, in video also they are able to identify, give image captioning nowadays. Okay. Now, we are done with the RNN architecture. We know that RNN is trained over every timestamp for an individual RNN cell, fine. Now looking at the advantages, yes, RNN remembers each and every information through time. Yes, because it has an individual cell, we say. Okay. But what are the disadvantages? Disadvantages, the first and foremost is the gradient vanishing and exploding problem. Most importantly, the gradient vanishing problem. And the other applications are training of RNN is difficult, a very difficult task. Okay, I mean, if you have very long sentences, paragraph, to find the sentiment of those sentences, in those sentences, it becomes very difficult for a normal vanilla RNN to do. And you can't process long sequences just by using TANH or ReLU activation functions. Now, the question is, given these disadvantages, how do we actually overcome them, or what are the solutions for them? First of all, before discussing the solutions, let us first find out what do you mean by gradient vanishing and exploding problem. So the first is the vanishing gradient problem. Since you guys know about neural networks and especially backpropagation neural network, in case of backpropagation neural network, what we say is that the error is backpropagated, correct? It is backpropagated, the reason being that we need to update our weights. Okay, we need to update the weights of the entire architecture. Now, for a simple artificial neural network with one input layer, one hidden layer, and one output layer, it is very easy for us to backpropagate the error. But in case of deep neural networks, you have stacks of hidden layers, one on top of the other. Okay, and you have not just only hidden layers, you can have even stack of neural networks also, different neural networks also together. Then how do you actually backpropagate the error? Because as the error keeps backpropagating, okay, you keep updating the weights, and at some point of time, the error will almost become zero. The error will almost become zero. So while training RNN, if your slope can either be too large or it can be very small, and this makes the training part very difficult. When the slope is too small, that means when the delta error with respect to one weight. With respect to one weight, that means that slope value, the gradient value, if it's very small, then the error almost becomes 0. If the error almost becomes 0, then that means we don't need to update the weights. When are weights updated? When there is error, right? Error in the sense, error is defined as the actual output, that means the target output minus the generated output, means whatever you're getting from your neural network. Error is that itself, right? If there is a difference between the actual and the generated, that means an error is present. But if the error is 0, that means what? The target and the generated both are same. Then we don't need to update the weights. The weights are fixed. But unfortunately, while this error is being back propagated using the red color line, it almost becomes 0 because you have those many number of layers. Okay, you have those many number of RNN cells. Okay, so it becomes a 0 by the time it reaches S0. Then what happens at S0? Whatever weight is there on X0, that is W0, that will not get updated because the error is 0. This is what we call as the vanishing gradient problem. Let's look at one example and then we can understand it much better. This is exploding gradient, which is completely opposite. Instead of reducing, error becomes larger. Okay, that's called as what they call exploding gradient. Now let's explain this using an example, especially the vanishing gradient problem. Now look at this, these two sentences. Consider the following two examples to understand what should be the next word in the sequence. That's the idea. You need to predict the next word in the sequence. So the person who took my bike and blah, 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 dash a thief. Okay, that's the first sentence. Then the second is the students who got into engineering with dash, 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 dash from Asia. Okay, you need to fill up the words inside both these sentences, either was or either were. Now, if you plan to fill up in the first sentence, if you want to fill up the word was, I mean, the person who took my bike and fled was a thief. Okay, that's the appropriate word that we will be using. We can't use were here, right? The reason why we want to, how we can fix it as was, is because we have to go back in time. That means we need to back propagate and check if it is a plural. Okay, if the noun is a plural or if it is a singular. If it was persons, then it would have been were. Since it's a person, it is indicated as was. Okay. So for this, what we did, we had to go back. Look at the cursor here. I'm going back, storing the information, again going back, storing the information, again going back until I reach the second word in the sentence. Right? In order to understand what would be the next word in the sequence, your RNN must memorize the previous context. Am I right? Whether the subject was a singular noun or a plural noun. And to memorize all this information, do you think it's easy? If I ask you to like tell me what you did in the past 3 days, what all did you learn in the past 3 days? You tell me exact word to word. Will you be able to tell? No. You can only just tell me a gist of or a brief of what you remember, correct? RNN also has the same problem. It can't remember each and everything. Okay, like how much can you create? Like how long can you create your RNN for remembering this? So when it reaches this particular point person, the error almost becomes 0. The same goes for this also. The students who got into engineering with the MPC degree dash from Asia. Okay. So you need to remember. So it might be sometimes very difficult for the error to back propagate to the beginning of the sequence. Okay. To predict what should be the output. What should be the output. And this is what we call as your vanishing gradient problem. Now, what would be the solution to the gradient problem? For exploding gradient, we have these three techniques. Identity initialization. Next is truncating the back propagation. That means only for some layers we'll do. The rest of the layers we will not back propagate the error. And the third is gradient clipping. Now coming to the vanishing gradient, first is weight initialization we start off with. Then choosing the right activation function, because so far we are only using tanh function, and tanh doesn't have that capability of remembering so many things. And using different, you need to use now different activation functions along with tanh. And so combination of different activation functions and changing little bit the architecture of RNN leads us to the solution long short-term memory networks, LSTMs. That means your vanishing gradient problem can be solved using LSTMs. So let's see LSTMs, but before talking about LSTMs, let's talk about long short-term memory. So why they are called as long-term, short-term memory is because they can handle long-term dependencies. Suppose we try to predict the last word in this text, that is, the clouds are in the dash. It is very evident and obvious that the clouds are always in the sky. They can never be in our head, right? So we don't need to like remember so many things, or we don't need to analyze so much. Okay, we can just simply say the clouds are in the dash sky. Where else will they be? Not on the ground, correct? So now the problem is, suppose if we have some sentence like this: I have been staying in Spain for the last 10 years. I can speak a fluent dash. The ideal word for this would be the language used in Spain. But for finding out whether, the word Spanish, to fill the word with Spanish, the word we predict will depend on the previous few words in the context. Now, where are these few words? That is this word. Spain is the word, right? Here we need the context of Spain to predict the last word in the, oh my goodness. Again, someone. Yeah, to predict the
Dear
last word in the
participants, sorry ma'am, sorry to
sentence.
disturb you. Dear participants, I'm requesting you again, please don't use annotation tool and distract that speaker, please. I'm requesting you.
Dr. A. Uday Kumar. Sir, you are using your annotation tool. Please, please, please stop. You are creating a mess on my screen. Okay, fine. So from going from Spanish till the word Spain, of course, there are so many words in between and you need to remember all of them. So it's possible that the gap between the relevant information and the point where it is needed becomes very large. And these are called as long-term dependencies, but LSTM has a very beautiful way of handling them. Let's see how it does. LSTM is actually a special kind of recurrent neural networks, like how what they call VGGNet, then AlexNet, InceptionNet are special types of CNN. So is LSTM. LSTM takes its influence from RNN itself, but it is a modification of RNN. And LSTM, it has a capability of handling long-term dependencies and remembering information for long periods of time. Okay. Now, in case of your normal RNN cell, we only had X1 going on to H1 and from H1 to Y1. And that was handled by TANH function. But in case of your LSTM, we have 4 activation functions. Yeah. LSTM also has the same chain-like structure, but the repeating module has a different structure. Instead of having a single neural network, there are 4, oh my goodness, again. There are 4 interacting layers communicating in a very special manner. So, okay, so now let's see what are these 4 interacting layers. 4 interacting layers are nothing but your activation functions which are incorporated inside each cell of LSTM. Okay, so this is the main addition in RNN. Then the basic RNN, these are the addition things. So long short-term memory networks, they comprise of 3 steps. The first step is called as forget in irrelevant parts of previous state. Second is selectively update cell state values. And the third one is output certain parts of cell state. This CT-1 and CT here, they indicate cells. They are not loss functions, which I was explaining to you in the beginning of the architecture. No. Here they are treated as cells, RNN cell, if you remember. So, yeah. Now let's discuss each and every step. It's quite simple, not an issue at all. Easily you will be able to understand. So, coming to step 1, that is decide how much of the past it should remember. That means forget gate. Okay, that's called as a forget gate. So the first step in LSTM is to decide which information is to be omitted and which information needs to get inside the cell. Okay, that is the first part. And if you remember, when I was talking about the food was really good example. In that example, I had mentioned to you that we ignore the words the food was, correct? Those 3 words can be ignored, and that is what your forget gate actually does. Your forget gate will ignore those words and only keep the useful information, which is your really good, or maybe say good. Okay, so that is what your forget gate will do. And to do this, I mean, which information needs to be sent, sent inside the gate, which information needs to be kicked out of the gate is decided by the sigmoid activation function. Your output of the sigmoid activation function is 0, 1. You get a probability value. So your forget gate mainly works on HT-1. That means your previous hidden layers output. It works on your previous hidden layers output and the current input XT. HT-1 and XT. On both of them, it will analyze and see if the current input is related to the previous hidden layers output. Means suppose I'm talking about RNN now. Okay. And suddenly I start talking about CNN. CNN has something called as convolution layers. It has something called as filters. It is used, it has many types of filters, many types of architectures. What I was talking previously about RNN and what I'm talking about presently CNN, they both are nowhere related to each other. So given a particular input, that means XT, it will be compared with HT minus 1 comparison, in the sense how much information from HT minus 1 can I take? Is it related to XT or not? That is what step 1 does. Again, another person. Okay. Kiran sir, please can you stop annotating? Oh my goodness. Yeah, this way I can, like, although it is disadvantageous, but still I understand, I can come to know that people are listening or fiddling with their mouse. Yeah, that's good. At least they're active. Okay, so now let's see with an example how forget gate works. These are the two sentences. HT minus 1 is the first. XT is this. That is, Alice is good in physics. John, on the other hand, is good in chemistry. This was the previous output which we got. That is HT minus 1 output we got as this. Next, John plays football well. He told me yesterday over phone that he had served as the captain of his college football team. This is your current input XT. Now I need to check if there is any relationship between XT and HT minus 1. Is there any relationship? No, no relationship. Yes or no? Okay. I think your madam
Yes,
has.
ma'am. It is, there's a relationship.
Okay, which relationship? Like, what is the relationship?
Like some part of the text, like related to John, it is related, but related to Alice, it is not related.
Kiran sir, please stop annotating. Yep. Yeah, the first and the second sentence, both of them are talking about John in different aspects, right? So that's what your forget gate does. Forget gate realizes there might be a change in context after encountering the first full stop. And that's over here. Okay. So there is a change in context. Till now it was Alice is good in physics, but now there's a change. Compares with the current input sentence XT. The next sentence talks about John. So the information on the Alice is deleted. That means this is kicked out from the forget gate. It says, Chalo, I don't need Alice. I only need information about John. So the position of the subject is vacated and is assigned to John. Okay. So that's how the forget gate works. Now let's look at how the second gate will work. Second gate is called as your input gate. It decides how much should this unit add to the current state. Means how much information should I use. Like even if I talk about RNN now, I'll be pretty soon talking about transformers, encoders, decoders, etc. But fine, out of all that, you will be only keeping information whatever is important to you, right? You will not remember each and everything. So in the second layer, there are two paths. One is sigmoid function and the other is tan function, tan-h function. Your sigmoid function, what it does is it decides which value to let through, that is 0 or 1. And tan-h function gives the weightage to the values. Even if it lets through, you need to keep in mind, like, what is the information that I really want to keep, even if it is coming through. Because in Ambani's marriage also, there were VVIPs, normal crowd, etc. But VVIPs were given more protocol, right? They were given more costly gifts. So that's what your input gate actually does. And Sigmoid function and tan h function are used. Input gate, it determines which information to let through based on its significance in the current time step. So let's see the example again. So consider the input xt. John plays football well. He told me yesterday over the phone that he had served as the captain of his football team. So input gate analyzes the important information. I mean, this was the input that we are given. In this also, we need to find out which is important and which can be ignored. So what it does is John plays football and he was the captain of his college team are important. He told me yesterday over the phone that is not important. Hence, that part is completely ignored. Okay, it is forgotten. So this is how your input gate now works. It gives importance that John played football and captainship. Rest is all nonsense. Then this process of adding some new information can be done via input gate. That's okay. Then step 3 is decides what part of the current cell state makes it to the output. That means based on this information that we have, like John plays football well, and he was the captain of his team. Earlier also, we were talking about in HT-1 also, we took information only related to John. Now let's see how this particular entire context of John can help us predicting the output. Okay, predicting the output for John. The third step, before talking about the prediction, I just quickly want to tell you about the third step. We run a sigmoid layer which decides which part, what parts of the cell make it to the output. Then we put the cell state through tan h to push the values to be between -1 and 1 and multiply it by the output of the sigmoid gate. Earlier we didn't have that, but now in forget gate, what we are doing is we're combining input information from the previous input gate and feeding it into the output because we require some output, correct? We need to predict some output. So we need to have information about the previous context. Previous context from where we got from the input gate. Okay, so let's look at the example once again. So this is our task or application. It says John played tremendously well against the opponent and won for his team. For his contributions, Brave Dash was awarded player of the match. Now you need to fill up the word inside this sentence, Brave Dash. Can any of you tell me what would be the correct word in the sentence? Hmm? Hmm? What could be the correct word? Brave dash. Correct word in the dash.
John.
Okay, why John? Why John?
Because we are talking about John, like he's the person he played.
Yeah, but apart from that, you also need to look at current input. Brave is an adjective, and brave.
Yeah, true. Brave.
After an adjective, the rules according to the parts of speech, it says you describe a noun, correct? And the appropriate noun that we have in this entire previous context is John. So John could be the best output after brave. So this is how your LSTM works. LSTM is able to handle your what they call long-term dependencies because it has an option of forget gate. It is able to analyze the information because of the input gate. And once you get the information from the previous context, you can use it anywhere anytime. And that's how your that's how your LLM actually works. Okay. So this is the first part of my lecture. And now I'll be moving on to the second part of my lecture, which is encoder, decoder, etc., transformers, which are the other advanced parts of LLMs. So, yeah, now can you tell me what would be the output of, if thank goes inside RNN, what could be the output? Nothing. Eh? Yeah, you. So, now, let me now share my screen. I think I need to reshare. Can you see the encoder decoder model?
No, ma'am, you stop that share and share that.
Uh-huh. Is this visible now?
Yes, ma'am, it's visible now.
Okay, so now these are somewhat the tricky parts, but these are commonly used in your LLMs, and that's what makes it interesting. Let's start off why we require encoder decoder. The reason being RNN does not work well, and that means in real world tasks, translating sentences from like "How are you?" In English, we say bagunnara in Telugu, which is completely one word. So those conversions can't be made. Someone mute yourself, please. నాకు అర్థమైంది. Sir, whoever it is, please mute yourself. Oh my goodness.
1 minute, ma'am, it's not coming.
I did it here. This is the problem when you have online sessions. So tasks like machine translation, summarization, question answering, all these have variable length input and variable length output, which your RNN can't really handle very well. And translating something like I'm hungry into Spanish is this one, 2 words. So it can't do this well. And these are your, this is your RNN architecture. And as I mentioned in LSTM also, it doesn't work that well. Now to handle this kind of problem where you have variable length inputs and variable length outputs, and those applications in particular, translation, summarization, question answering, sentiment analysis and all, you tend to use encoder, decoder. That's the basic actually. So the encoder decoder model, it solves the variable length sequence problem by separating the architecture into 2 parts. One is called as the encoder, the other one is called as the decoder. Now, what happens here is, in case of encoders, we convert the words into something called as word embeddings. In, the most advanced architectures, neural architectures, we convert all the, what they say, words, actual words into something called as word embeddings. Either you can have one hot encoding, one hot coding scheme, or either you can put it into word embedding form. If you put it into a word embedding form, you can come to know the relationship between one word and the other word also. Okay, using word to vec. Then you have other techniques also, continuous bag of words model, etc. So what happens is encoding does that. It reads the entire input sequence and compresses it or encodes it into something called as a context vector. Okay, into something called as a context vector. The entire word embeddings, all the word embeddings, in fact, all of them are converted into context vectors. And decoder, what it does is, it takes these context vectors and generates the concerned output. Okay, takes the context vectors and generates the concerned output sequence. It can be of different length than the given input. And this actually helps in our sequence to sequence modeling. And this is how your encoder decoder architecture looks like. X0, X1, X2, all of them are plain words. And when they go into the encoder architecture neural network, they are converted into word embedding. Word embeddings together of different words are converted again into a context vector. And that is your hidden state here. That's your hidden state. And the output from the hidden state is then fed inside decoder network. And decoder network, it has its own methodology, and it gives you the concerned output y0, yn, so on, y3. Now, what are the components of your encoder decoder model? Encoder actually, it takes the entire input sequence and encodes it into a single vector called as context. And this is done using RNN, LSTM, etc. And decoder, it starts with the context vector and generates the output sequence step by step. That means it decodes first word in the context vector, then it decodes the second word in the context vector, then it decodes the third, so on and so forth, one word at a time. And what does your context vector do? It embeds or encapsulates the meaning of the input sequence in a fixed size vector. Please remember this, the context vector is of fixed size. Okay. And the entire sentence meaning, that is word embeddings, everything all together are fed inside the context vector, and it will have the meaning of the input sentence. Okay. And this is how your, based on RNN, this is how it looks like. X1 is given to RNN, X2 is given, so on and so forth. Then you get an encoder vector, and that encoder vector or the context vector is given into RNN again in order to generate the concerned outputs. For machine translation, this is how it looks like. The words are, as I mentioned, the words are converted into word embeddings. English needs to be converted into French. Don't ask me to pronounce the words in French. Huh? I don't know French. Okay. So these are the context vector weights. These are fed inside the decoder, and decoder will do the translation part, the appropriate translation into French, and give the concerned output in French. Some of the applications of other applications of encoder are text summarization, speech recognition, image captioning. Now, the problem with the encoder decoder model is that you have a fixed length context vector. Okay, the fixed length context vector. I mean, this is a problem. I mean, for long input sequences, it compresses everything into this much size of fixed length of context, fixed length of vector. So this is a problem. I mean, you can lose some information also, some information related to the input sequence. So this is the main problem. Like for example, the quick brown fox jumps over the lazy dog. So if the vector is too small or the sentence is too long, keywords like fox or lazy dog, they might be ignored. They can also be misrepresented during the translation part. So what is the solution for this? Attention. Okay, so attention mechanism allows the decoder to look at different parts of the input sequence dynamically during decoding. Okay, and what happens here is that when I have a input sentence, okay, and we have created a context vector to it. Along with the context vector, your decoder also looks at the input sequence. Okay, this is the word. Is it being correctly represented in the context vector? Yes. Then, okay, decode it. Then this is the word in the input sequence. Now, is this being correctly represented in the context vector? No. No, then again, send it back to the encoder. Let it again change it. Let it again create a new context vector. So this is how your attention mechanism works. Attention is also given to the different parts of the input sequence. So rather than relying on the single context vector, the decoder dynamically attends to different parts of the input sequence at each and every step. It is nothing but it is comparing context vector. What is the input in the context vector? Is it same as the input in the input sequence? That is how decoder is working. At each time step, the decoder assigns different weights to each hidden state of the encoder. Okay, and it focuses on the relevant parts of the input sequence for generating the next token. And this actually, it impacts the overall performance on long sequences when you have long sequences, because that information needs to be saved. Okay, important information needs to be saved, right? So that is how attention helps you in doing it. This is how it looks. I just want to have a sister. No, I don't want a sister. Fine. Okay. If you notice the bold line, bold curve that you're seeing, it's paying attention to each and every point. Like wherever it is necessary, it is giving you that particular importance. Okay. And this is the architecture attention mechanism. Attention layer is added in between. Now, there is a problem even with attention. That is like, if you notice in this particular diagram, it is only happening sequentially. It is only happening sequentially. That is, I, then want, then just, then have, then a, then system. Like that, one by one, one by one, one by one. All the words in the English sentence are being connected with the French words. Okay, but how many times will you do this if you have a long sentence for each and everything? For each and every word, should I check, is this related to this word in the input sequence? Is the same word related to the other word in the input sequence? You can't keep doing this sequentially. So to avoid this or to solve this problem, we use something called as self-attention. Okay, so in case of self-attention, instead of focusing only on the relationship between input and output sequences, a concept called as transformers, it uses self-attention to model the relationship between all parts of the input sequence at once. So what are transformers? Transformers actually were developed to remove RNN capability completely. Means you don't need to use RNN at all, eliminate RNN at all. They rely mainly on the mainly on the attention mechanism. But what happens is they have made a little modification to it by adding self-attention. So in self-attention, each word in the input sequence can attend to every other word, okay, allowing the model to learn relationship between all words at once. That means instead of having a relationship I with the French word je, and I with so, and so on and so forth, parallelly. Okay, parallelly, I will be compared with all the French words. The just will be compared simultaneously with all the French words. Want will be compared with all the thing. And at the same time, you would be having a relationship between all the input words in a given sequence. Okay. That is what we call as self-attention and multi-head attention. Instead of using a single attention mechanism, transformers use multi-attention heads. That means sometimes I, sometimes just, sometimes want, all these together will be compared simultaneously with the inputs or with the decoder outputs. Okay. So this is what we call as self-attention and multi-head attention. Self-attention is when we have a relationship between the words in the input sequence, and along with that we are parallelly we are introducing parallelism into what they call translation part. Okay, that is called as multi-head mechanism. Now, for these two to work simultaneously, since we have removed RNN earlier in transformers, we require a new technique. I mean, how do we know after an adjective a noun should come? After an adjective, we shouldn't have a verb. We need to even have such kind of rules and regulations also in mind in order to form a meaningful sentence, syntactical sentence. And this we are doing using a technique called as positional encoding technique. Since transformers, they don't have a built-in sequence model like RNN, positional encoding, it is added to the word embeddings to provide information regarding the position of each token in the sequence. Now, how is this done? Let's see that later. But this is the architecture. I'm not going to delve into much of it. Input embedding, positional encoding is given here, multi-head attention, addition of layers, normalization of layers, feed forward, so on and so forth. You get the output probabilities fine. And this is the architecture of your transformer. Okay. Now, self-attention basically works, I mean, in order to understand positional encoding, what they call, you require to know about self-attention, how it works. It works on 3 tokens, which are query, key, and value. Okay. So the model computes the dot product between the query and the key vectors to get the attention score. Means if this is the word that I want to find out and this is the key that I'm given, we need to combine both of them and calculate the attention scores, which will tell the model how important each word is with respect to other words. Then the attention scores are used as weights, okay, which become the output of the self-attention mechanism. Now, self-attention provides a way for the model to understand which words are most relevant and which words can be ignored. And this is how it looks like. Okay, softmax, because it's giving you, it's a multi-class classification. It will give you the concerned output itself. Okay, so for encoder, you have self-attention. For decoder, you have self-attention. And that's how your self-attention mechanism works. Then multi-head, the input is split into multiple heads like I just now mentioned. And this is the architecture. Now positional encoding, each position in the sequence is assigned a unique encoding based on sine and cosine functions. That means if it's even, it is sine. If the location is even, then it is sine. And I think if it's odd, then it is calculated using cosine functions. So these positional encodings are added to the word encodings. That means along with the word encoding, you also know that this word is in even position. This word is in odd position. So in the sentence, the cat sat, the positional encoding ensures the model knows that the word the comes before cat, and sat. That is what your positional encoding does. It puts them into orders based on what they call their values. And this is the what they call equations. P position comma 2i. I is nothing but the word. Okay. Now, this is how your positional encoding works. Now, there is still little problem of your what they call transformers. That is like how can you make transformers better? Okay. So to make them more better, they have created architecture called as BERT, which only focuses on the encoder part of your transformer. Transformer was made up of encoder and decoder, but in BERT, we only use encoding neural network. So BERT is a combination of bidirectional LSTM with encoder architecture. Okay, so it stands for bidirectional encoder representations from architecture, from transformers, sorry. So we are taking encoder representations from transformers using bidirectional LSTM. That means the output from the last by layer is fed again as input to the previous layers, feedback system. Okay, so the key difference is traditional models RNN process sequence left to right, but BERT, what they call processes bidirectionally from right to left as well as left to right. Why it matters? The reason being that all the words can be taken in one sequence in one go itself and can be processed in one go itself. That means the computational time complexity reduces. I mean, the time for training reduces because till transformers, what we did was one word, another word, one word, another word. Like that, we kept doing one word at a time. But now, no, we'll take all the words together. BERT takes all the words together, performs query, key, value functions on all of them, does positional encoding on all of them, all at the same time. Okay, why? It improves the performance, means you don't take much time to do it, correct? So how does the BERT work? BERT works only in two ways. I mean, even if it takes the entire context also, it only has two functions. One function is masked language modeling, and the other function is next sentence prediction. So if this is the sentence, the cat sat on the dash, that the dash means it is masked. You need to predict what is the word. So BERT, how it will predict is it has a pre-trained model. It has a pre-trained model which comprises of training on different words in the corpus or in the vocabulary. So using the previous vocabulary, it will easily try to predict the missing word or the masked word, which is MAT. In case of next sentence prediction, you try to find the relationship between sentences. Given two sentences, BERT predicts if the second sentence is logically connected with the first sentence or not. That means RNN is so and so, CN is so and so. CNN is nowhere concerned with RNN, correct? So there is no logical connection. If I say RNN is so and so, LSTM is so and so, then that means these two sentences are logically connected with each other. So the next sentence prediction, which gives you a Boolean value, Boolean 1 if both the sentences are logically connected, Boolean 0 if they both are not connected with each other. So for both these masked and next sentence prediction models to work, we have what they call pre-trained neural network, pre-trained RNN or LSTM. Okay. And using those inputs only, it will be able to give you the masked output or next sentence. And input actually is given starting with CLS. When it gives you a CLS, basically it says starting of a sentence. Okay. And SCP here is another word which is inserted, keyword which is inserted. That indicates it's a separation. That means next sentence is going to follow. Okay. So this is how your input is given. So along with the normal sentence, you will first add CLS, that is starting of classification. And next is SEP, which is starting of next sentence. So you have position embeddings, segment embeddings, token embeddings. Okay, all these together fed inside your BERT. They are all these are part of your BERT. I just now had told you, we use self-attention, we use multi-head attention, we use positional encoding, etc. Okay, so this is how it works. How are dash doing today? So you either need to say you, they, your, etc. Whichever has the highest probability, that will be taken as the masked word. And as I mentioned, for BERT to work, you require pre-trained models and fine-tuning. Why we do fine-tuning is because we already have pre-trained models for the concerned task, whatever task we want to perform. Okay. For that task, we will be fine-tuning the existing model according to our task. Like text classification may, how can we change the parameter values in order for it to give text classification? Same goes with question answering, etc. Okay. So this is how your pre-training and fine-tuning actually works. Why BERT works better? Because of the bidirectional context, and you have transfer learning. That's what pre-trained means. And you get state-of-the-art results like question answering, sentiment analysis, and all. And these are some of the applications. And thank you so much. I'm done with my lecture. Yeah, I think I took 8 minutes more.
Okay, ma'am, no issues. I invite participants to give feedback in any few words, please. Any queries? Otherwise, participants, I invite participants to give feedback in a few words, please. 1 second, I'm giving. You can unmute yourself and you can give.
Yeah, good evening, ma'am.
Hi.
Ma'am, please switch on your video, ma'am.
That's all right, even
Thank you,
if she can't.
Hi, it's coming on.
Good evening, ma'am. Yeah, today really it was a nice presentation. We learned many things from your PPT, ma'am. Really, the wonderful way you prepared the PPT, also the presentation. And today, I would like to thank ma'am to clear all the doubts. Actually, we had some doubts in the activation functions, but so from your class, that is also cleared. And today we felt like this is not a virtual class. We felt like it's in a the face-to-face the class with. Really, it's a wonderful session, ma'am.
Okay, thank you.
Anyone else? Otherwise, we'll take a few photos. Can you please switch on your cameras? Dear participants, can you please switch on your cameras, please? We'll take two to three photos, please.
I'm Ganga here. I also would like to thank ma'am for her session. I could really understand the concepts very well, and especially the even the LSTM part, like each cell, each step output, right? Input and output. It's not that clear in any of the books or whatever material we have read, but it's very, very clear with very clear examples. So thank you so much, ma'am.
Thank you, Ganga. Anyone else? Sir Rambabu sir, can you please take photos, please? Please switch on your cameras. Dear participants, please switch on your cameras. Rambabu sir, done?
Done, madam, done.
Okay, thank you, sir.
Thank you.
On behalf of the entire organizing team, I would like to thank Miss Dr. K.V. Kadambari ma'am for gracing us with her presence today. Your valuable insights and time have made a significant contribution to this event, ma'am. Thank you so much once again, ma'am. Thank you, ma'am.
Thank you. My pleasure. All the best.
Thank you, ma'am.
Thank you, madam.
Okay, sir.
Thank you, ma'am.
Yeah, my pleasure. Where do I sign out? I don't know. Is there any end button? Leave button is here. Okay. Bye, guys.
Bye, ma'am.
Have a nice evening.
Thank you, madam. Thank you so much.
Bye, madam. Wish you the same. Thank you.
Thank you. Bye.
Dear participant, we'll take short break, 2 minutes break. Already speaker was joined. Please take short break, 2 minutes break, please.
Hi, Rambab sir. Hello.
Hello, madam. Hi, madam.
Yeah, is my voice clear, sir?
Clear, madam. Voice.
Yeah. I want to check whether I am able to present my screen. Okay, we can utilize this.
Ma'am, you can share and you can test, ma'am.
Yeah, I want to share. So
I'm going to stop that sharing, ma'am. 1 second. Then you can.
Okay. I'm sharing. Is it visible?
Yes, ma'am. It's visible.
Yes, madam.
Okay.
Yes, madam. Clear.
I will put into presentation mode. Yeah, I think.
Yeah.
So slide navigation also visible, right?
Yes, ma'am.
Okay. Thanks for confirming. Then we can start in 2 minutes. Yeah.
Yes, ma'am.
Okay. Yeah, Anusha.
Yeah, ma'am, we'll start. Okay, welcome back, everyone. We are now ready to begin session 2 of day 4 of our FDP program, the revolution of LLMs in AI. Now I want to give the mic to Ms. Uma Maitri, ma'am, to introduce our honorable guest of session 2. Over to you, ma'am.
Thank you, ma'am. Once again, good evening, one and all. It's my immense pleasure to introduce our today's guest, Dr. V. Sirisha. Dr. V. Sirisha is a distinguished data scientist with expertise in natural language processing, machine learning, and large language models. Her work includes building advanced recommendation systems and designing graph-based solutions to model complex relationships, delivering impactful business results. She has contributed extensively to innovative AI products like knowledge graphs, question answering systems, and interactive learning companions, leveraging state-of-art embedded models and frameworks. Her research spans across cutting-edge AI technologies, including large-scale transformer models and graph analytics. And she has delivered corporate training sessions on graph analytics and knowledge graphs. Dr. V. Sirisha is passionate about mentoring and guiding teams, improving state-of-art methodologies, and driving AI solutions that create measurable impact. Her strong background in experimental design and research methodologies reflect her dedication to advancing the field of data science. I humbly request Dr. V. Sirisha to take the proceedings of this session. Over to you, Sirisha, ma'am.
Yeah, thank you for the detailed introduction. Yeah, very good evening to all of you. I hope my voice is clear.
Yes, ma'am, it's audible.
Yeah. Let us make this session little bit interactive. The earlier session, ma'am has given a elaborative background of what like state-of-the-art LLM models. So the architecture of transformers and also the attention mechanism. These all things are the basic understanding is required in this LLM era. So let us make this session little bit interactive. So I am planning like we will have some discussion segments. Is it fine, Rambab sir? We can make it little bit interactive.
Okay, madam, no problem.
Yeah, so so that we can have some thoughts from the from all the people here who has kept some time and commitment to to involve in these sessions. Okay, yeah, in this 1 hour or so, I will share with you how the NLP or LLMs are they are how in the real world they are able to address healthcare challenges. So before jumping into how they are able to solve healthcare challenges, let us have some. No, I want to start this session with some like case study or some story. Oh, so that we can know from this no narration the role of NLP in solving the real world challenges, and also I want to drive forward how this NLP or LLMs are transforming challenges. So here I want to take a case of John. So this is just for a narration. So like John is a 50-year-old man, and he has history of hypertension and diabetes. So please don't mind that I'm starting with this example, because this example is apt to show the technology, how technology really helps in solving these medical problems. So that's why I'm starting by taking this case study. So he has a history of hypertension and diabetes, and he has also he is experiencing fatigue as well as shortness of breath. So that's why being having this kind of symptoms, he decided to consult a doctor. But his journey is very bad because he has some because he has gaps in communication, and also the data management, and also the patient engagement. So first thing is John's symptoms were very no difficult to describe during the consultation, because his very bad situation, and also his medical records were scattered because they are not in one place, they are scattered across hospitals. That is leading to missed insights, and he is not in a position to describe his situation. And also he struggled with understanding, so what the kind of treatment plan and what are the follow-ups. These all things he is really struggling. So this is a scenario. Now let us take it forward, how we can help John using our NLP or LLMs. So like not only for John, in many, like in day-to-day life, in healthcare industry, and in any other domains, we will be facing these kind of similar challenges, and how like actually the technology should help to solve the real world problems. Yeah. So so now we will transition to the how we can help John using NLP first, and later on we will go to the LLM models and what are the limitations of an NLP and why we should go to the LLM models. So before jumping into that, let us have some code snippets as well as some of the NLP fundamentals. So when if you see here, first John described his symptoms to the doctor. So he is struggling with shortness of breath, and now we can use NLP, and we need to step with NLP here to analyze his words and identify the patterns in clinical language. So how that will help, we will proceed further. So before jumping into the solution for how this NLP will actually solve, we want to know some of the fundamentals. I think enough background is covered in the earlier sessions, but just we will narrate that fundamentals and the theory we have learned with some code snippets as well as solving some real world medical problems, how this actually helps. So NLP is nothing but it will enable machines to process and understand human language. So if we see NLP, the key task involves tokenization. So we will see, like we will cover, at least we will spend 10 to 15 minutes of time in knowing what exactly is tokenization and what is parts of speech tagging and NER, sentiment analysis and text classification. So I want to analyze these and correlate with the like examples and code snippets. So if you see now again how NER or text classification or summarization can help John's case. So NER, using NER, we can analyze John's medical complaints and we can identify or retrieve the key symptoms. And also we can classify, we can, by using text classification, we can categorize his symptoms into clinical terms. And also he has health history from diverse records. So we can summarize that so that the time for the clinicians also will be reduced. That's how summarization can help John to make the case fast. So yeah, now let us jump into some of the code snippets. So we learn like tokenization is nothing but dividing into n number of sentences or tokens. Actually, this session, I want to get a feel of how we can implement these concepts actually. I think many of you might be familiar, but so here I have taken some examples related to medical domain as well, so that it will help us to understand how actually we can solve this problem. If we see here, NLTK is a popular and well-known library for NLP. So here we have tokenization, where if you see here, I have taken a synthetic data to make the things very simple in each code snippet. So here we are assigning, no, I feel tired all the time. So these are some of the symptoms that John narrates, so health compliance. So what we are doing as part of the tokenization is nothing but dividing the sentences. So here we are the sentence tokenization and word tokenization. So that is what we are doing by taking a simple textual sentence. So like in NLTK, we have already, NLTK is a predefined library, that is a natural language toolkit, where we have a tokenized method. So we are importing the word tokenizer as well as sentence tokenizer. So we are taking this, like synthetic data of John health complaints. Then we are dividing that into sentences as well as words. So Yeah, actually, this is the output of this particular synthetic data. So what the NLTK did is using the methods. It is divided into sentences as well as word tokenizer divided into words. So how this tokenization helped in our in solving our use case? So it prepared the clinical notes or patient complaints for further analysis. So tokenization helps us to make the further analysis in a better way. So that is how, like in NLP, tokenization help in this scenario. Likewise, if we take NER, so NER is nothing but named entity recognition. So where we can identify the entities. Like in this scenario, we can identify the symptoms as well as medications as well as diagnosis. So it will help us like in a one go, we can identify all these things using NER. So we have another popular library in that is Spacey. So using Spacey, we can invoke this NER, and later on we can identify the entities from the given string. So here I have taken the same sentence synthetic data set, and for this data set we are converting, or we are retrieving the entities from the medical synthetic data set. So actually, like if you see, shortness of breath is a symptom. So here how this actually NER can help John is, so it helped to extract symptoms or conditions from unstructured patient complaints. So that is how NER helped here. Likewise, text classification is also a very good problem in NLP. And one of the well-known library related to the machine learning algorithms or NLP algorithms is scikit-learn. So it has like almost all the classification, regression, and association rule mining. So those kind of all algorithms are there. So here I have taken now from the scikit-learn I have taken the Bayes classifier. And here also have taken the sample synthetic data sets related to the medical domain. And we are taking the labels as symptom, treatment, and symptom and treatment like this. And we are training the model so that whether it is able to classify correctly or not. So here, after converting into vectors that particular sentences, so I am asking the model to predict. So what is the category it belongs to? My legs ache and I feel dizzy. So whether it is a symptom or a treatment. So here, after making the model learn, so these are just a code snippets that helps us to understand. So this is not a complete code, but in the real scenario, we will have like we need to scale, and also we need to fine tune our models. Those are all things we need to do, but these are only for understanding sake. And if you see, we are able to predict the category that is a symptom. So here we are able to now using this text classification, we are able to like convert that patient complaints into actionable intelligence. So that is how we are using the text classification scenario here. And one more important topic that is has well researched, and also in industry also that has gained importance in many use cases is sentiment analysis. So here in our case, as we are applying NLP and LLMs in the medical domain in today's session, so how actually sentiment analysis is solving problem here? So here, if we want to understand the patient's emotional tone, that is whether positive or negative or neutral. So here I have taken like text containing, I feel so exhausted and worried about my health. I want to know the sentiment. So for this, we are analyzing. So we using our model, it is able to detect whether it is a positive sentiment or a negative sentiment. So like how it is relevant for our use case that related to John is it helps to gauge the patient's emotions, as well as we can enhance the empathy in care. So this is how actually NLP concepts are used here to test whether the sentiment, like the patient's emotions, we can get a retrieve out of this sentiment analysis. So not only in terms of healthcare, but also in other domains also sentiment analysis is very important. So whether we want to know about the product review. So whether the product is rating based on the reviews, we will be in e-commerce as well, in Amazon or Flipkart or any other e-commerce. We will be writing many reviews about the product. So lot of business going on, whether that related to the product, whether the customer is satisfied, positive or negative or neutral, and also like many recommendations will be given, and lot of recommendation algorithms has to be written there. So in that case, NLP actually helps in not only one domain, in other domains as well. And as ma'am covered in the previous session, so vectorization, so that is nothing but embedding. So we will be so we want to make computer understand the natural language. So vectorization is nothing but we need to convert, like the natural language should be converted into numerical representations for machine learning models. So we want to convert like words into numeric vectors. So that is a very important thing, like in this LLM era. So because a lot of transformer models, so they are contextual based models. So actually we need to understand the transformer architecture and how the learning, what is attention mechanism, and how the like we are able to unlike a bag of words model that I will be explaining in the next coming slides, how we are able to retrieve the context nowadays. So here a model can't process the raw text. So that's why vectorization allows us to represent sentences, words, or documents mathematically, and still they will preserve the semantics. So they will be represented in the form of matrix or vectors, and then the algorithm will know the context based on the transformed architectures nowadays on latest embedding models, or and also in vector DBs, and in latest frameworks like RAG or LangChain. So this is a very important concept, fundamental concept in order to solve the latest use cases. And as I told, so what are the types of vectorization techniques? So earlier, if you see bag of words, and now ma'am covered in the earlier session enough information related to transform-based embeddings. But now earlier, if you remember, and we used to use bag of words model, but they are just we used to represent text as a collection of word counts or binary, but a bag of words does not capture the word order also. So next we used to use TF-IDF, that is term frequency, and inverse document frequency. We used to weigh the words and give the importance in a document related to the corpus, so based on the frequency of words. And the later on, that is a basic vectorization. And now if you see in the advanced vectorization, we used to have this word embeddings, so a word to vec and glow. So they will capture the relationship between words. So vectors for king and queen, they will have the similar properties, and also based on the context, and now transformer based embedding models like BERT or GPT, so they are based on this models. They can generate the contextual word because they are based on the sequence to sequence models like RN, and also the transformer based models with self-attention mechanism, where they can learn, and they have a cross encoders architecture where they can retrieve the meaning of a word depending on the context. So this is a simple introduction related to the types of vectorization techniques in NLP. And yeah, let us take this code snippet. So this is also related to the healthcare. I have taken, let us suppose each like 3 documents, but I have taken 3 sentences. But each sentence contains like patient reports severe chest pain and shortness of breath. So these all things this is a sample synthetic data set we have taken. And just this example, this code snippet will help us to understand how these sentences are converted into vectors. So like if you see document 1 means sentence 1, these are the values, and document 2, these are the values. I'm not going to the theory behind it. Almost like enough theory is covered in the previous session. So how actually the values are retrieved and how this NLP, this is textual information, is converted into vectors. So like that, we are again taking the scikit-learn feature and TF-IDF vectorization and able to get the values. So this is the output for that code. And what we can interpret from the output is, if you see like words like chest and pain appear in multiple documents, and they have relatively low score because of the commonality. And if you see fatigue or reports, they have higher weights because they have their unique words, and they have higher weights in the respective documents. So like this, we can interpret the output from that particular code. And also, yeah, how this vectorization actually helps in the real world. So if you see a symptom analysis, so if we use embeddings or like TF-IDF or any other Word2Vec or GLOW, using that embeddings, we can prioritize the clinical symptoms based on the frequency and importance. So that is one thing. And it's like this is total TF-IDF is totally based on frequency. So like that, it is useful in terms of capturing the importance across the patient data. Likewise, if you take this document similarity, this document similarity will help to find the similar patient cases, because here in document similarity, what we will be doing is we will be like how I have taken the documents, like so here I have taken the sentences here, but we can take n number of documents, and later on we can create that documents into embeddings, or that is vectors. Then we can find the similarity. Like we have many similarity metrics like cosine similarity and Euclidean, Jacquard, dot product. So these are many similarity metrics available. So once we get the embeddings or the vectors among n number of documents, so we can we can ourselves build some small POC kind of things and demonstrate to our students. So by taking a small like synthetic data sets, that's why I'm giving some ideas to you. So if we have some documents, like we can create, like medical documents are little bit confidential. If you're able to get them, that is fine. Otherwise, we can create our own synthetic data set using GAN kind of architectures or other neural network based architectures, and get the synthetic data set. And later on, we can find which patient cases are similar. Not only this, if I want to cluster the behavior of some students, and also I want to know what is the interest of behavior of some people, the likelihood of purchasing the same items. So these kind of things, all I want to compare two documents, how they are similar. So we can just simply take those documents and store them, and like in vector DBs nowadays, they are very popular. We can store them, and we can transform, like we can create the embeddings and store them in a logical way where indexing will be there, and we can use them in a kind of question answering mechanism also. And we can compare the how similar the patient cases are. So that is use case here. Likewise, we can use the same approach in n number of use cases. And also, if you see text summarization, like nowadays, if you see research papers also, just we will see the abstract instead of the whole paper. So we can get the summary of the entire paper. Like that, we can capture the context relationships, and we can create summaries using the embedding models. So that is how text summarization can really help. And yeah, now we will see how in this John story, how this tokenization or NER or text classification or sentiment analysis, these all things actually how they will help. So if you see tokenization, they will enable the segmentation of John's complaints into manageable units. So how we have done, like if we go to the tokenization part, we have taken the synthetic data set related to John, and we have divided that into words and sentences. That will help us as a manageable unit for further analysis. Likewise, if you take NER, so we can we can extract the key symptoms like shortness of breath and fatigue from the whole descriptions. And also we can categorize using text classification his complaints, like whether high priority symptoms which has to be taken immediate attention. Likewise, we can detect the sentiment analysis of that particular person, whether detect his anxiety and worry, and based on that, doctor can act accordingly. He can provide some empathetic actions on that particular patient. So that is how NLP can actually help in this domain. The same concepts or the same code snippets can be applicable to other domains according to the use case. We can do that. So now with this, I want to summarize this NLP. So actually how NLP techniques, if you use tokenization or NER or text classification. So we use NLP to extract some actionable intelligence from unstructured data, and also we can use them for operational efficiency, and also we can enhance the patient care through accurate decision making, because we can have we can use all these kind of embedding models, and also text summarization and NER tokenization. These all things we can do, and we can come up with a quick and accurate decision making. So with this, I want to make I want to give some points, take some points from the participants. So I want you to put in the chart, like these are the two discussion points. So what approach would you take to analyze unstructured data, text data from patient feedback forms? So you have, let us suppose you have some feedback forms from the patients. So which is the approach you will take? Now, you can think, and some people can unmute yourself and and also discuss these points. And also I want to another discussion point is how actually NER can transform patient record analysis in hospitals. So these two, I want you to express your views. Anusha, is the discussion point clear?
Yes, ma'am.
Yeah.
Yes, madam. To analyze the unstructured data, we can use no MongoDB, or NoSQL or MongoDB. We can able to use that one to convert into structured data. That is to handle that one. And named entity recognition means here that is based on the what exactly. Suppose we have taken the John Mitz, that is one taken. He suffering with the diabetes and hypertension. Here hypertension and diabetes are the named entities, and also relating with that one, he is suffering with the fatigue, and also we have written fatigue, some more things that is relating to that one. Then based on that one, we can able to say that is named entity recognition purpose. We can see that one.
Yeah, thank you. And also, you told like MongoDB to store, but what you are able to retrieve from the feedback forms. So how NLP actually helps in that? So
actually, yes, based on the that is what we have identified by the named entity recognition. Named entity recognition, what we are storing, that is only based on the health record, means hypertension and diabetes, that relating to the what fatigue, and he is unable to, that is dizzy, and some more things, that is those words only in the MongoDB, those words only mapping with that one. From that we can able to retrieve the data from the MongoDB or NoSQL database.
Great.
Based on that, we can.
Yeah, great. So I want others also to participate and share your multiple thoughts. At least from women faculty, some people. One more. So just nothing like we can, if feedback forms means for students also we will be giving feedback forms. No, so what will be, we can do some kind of sentiment analysis, right? So I'm giving some more hints. I want you to participate. Just like it is not like a one session. At the start of this session also, I told that it should be interactive. Just we are sharing our thoughts based on the kind of products or the use case that we solve. So likewise, I want you people to share your experiences, like given some not only patient feedback forms. So how are you able to use NLP and extract some insights
Ma'am, this is Zakir Hussain. Regarding the patient feedback form, I mean, we can do a sentiment analysis on it. And based on the sentiment analysis, the points that we get on the positive or negative, if both are equal, then I mean, unsatisfied or I mean, some weightage should be given on the positive and negative. And based on that, we can derive whether the patient is happy on the service or not.
Yeah. Yeah, actually, it is important, right? Thank you for the answer. So, actually, it is important to understand the feedback from the patients, whether the facility is fine and how the treatment is, everything. Especially, that is a very important domain where the attention should be taken utmost care. Even if we take kids also or adults also, they should have very good experience. So the feedback form helps. Thanks for the answer. And I need at least one women faculty member. Yeah, or anyone. So we have other MCQs also. Your voice is not clear. Anusha, you are able to hear?
No, madam.
Yeah, someone not talking.
Hello, ma'am.
Yeah.
Initially, we can do the pre-processing methods by using tokenization, stemming, lemmatization.
Nice.
And after that, we can convert the important text into word vector conversion, word to vector conversion.
Yeah.
And then we can apply any classification method to classify whether the particular disease is there or not.
Yeah, please.
Switch on video, madam. Vidilata, madam.
Haan, sir.
Switch on video and ask, madam.
Ma'am, you can switch on your video.
Shirish, not you, madam.
Yeah, I switched on the video, right? Yeah. Yeah, actually, Ramap sir, I'm able to understand her. What is her name?
Vidyulata, ma'am.
Okay, nice. The good answer. Yeah. Yeah, sir, shall we proceed then? I think they are able to answer and they are able to involve.
Ma'am, I have one doubt.
Yeah, please.
Ma'am, exactly if any text input we are taking, if it is a vocabulary word, we can able to easily identify. So how can we able to identify out of vocabulary words, ma'am?
So that's why we are out of vocabulary also. We have LLM models. Like if you see earlier, we have bag of words and also the other models which does not capture the context. But if we use like now we have one research paper like related to embeddings. UAE Lodge and like leadership dashboard, we have one embedding models. They have trained on the large corpus so that they can understand the context out of the vocabulary also, because they are trained and on this attention mechanism. So the, and also from the open corpus and also if you see like some of the models like UAE Lodge and BG Small, you can refer these models. So these are state of the art embedding models where they have this sequence to sequence model as well as the cross encoder mechanism that helps them to learn out of the vocabulary, and also they can learn the context out of that. So now the architecture is designed like that, unlike the earlier embedding models. Yeah, and also from the previous lecture, you have seen, no, ma'am has given a architecture based on the transformers. There, she has shown the flow of the entire transformer. So that is how the learning will happen. Yeah. So any other discussion point?
Hello.
Yeah.
Yeah, ma'am, I have a doubt.
Yeah.
Ma'am, what if there is any spelling mistake in the feedback form? Suppose the patient is not writing the accurate word. He's missing some letter or word, and then it will incorrect the explanation or feedback, or the incorrect explanation will give wrong feedback form, and then it will harm our data or something like that.
Yeah, that is a good question only. But now, like auto correction and these all mechanisms we have, like this problem is solved like few years back, long years back. Now with the advance of this technology, we have auto correction models. So Grammarly, these all many NLP tools are there. Grammarly is one best example, right? So they can auto correct that, and also there is one problem here. So I am not saying that LLMs can solve everything. So as you told, if if we have lot of spelling mistakes, or if we have a lot of misinterpretation of the data, definitely LLMs also will give some hallucinations. So that's why no model, we can't say that we have got 90%, 99% accuracy, because these all things. And also when we are developing these kind of mechanisms, we will do lot of pre-processing and post-processing. We will make sure that so we will do this NER, and also we will map that POS tagging. So these all components we will be doing, and we will be doing a lot of post processing also. Once we analyze the information, so there also, if any words, like as you told, some synonyms may be taken as understandable by the model as a different way. So like that, we need to train on diverse number of documents, and make sure that we need to see like this problem can be solved by the concept called word sense disambiguation. So in that, what it will do is it will sense the word, whether the spelling is correct or not. Then it will auto correct it when we enable that feature, so that the pre-processing will be done accurately. And definitely at that time, the feedback form will be taken, the context. That is, if you do few short learning, if you use LLM models, or if we do sentiment analysis by converting that into no correct embeddings or vectors. So before doing itself, we need to take care of all these techniques, and then only we need to feed the model or train the model with the correct information. So this is very important question. So not only related to the spelling mistakes. So there may be cases like we will be using some synonyms in one context and some other words in another context. So that's why we should be very clear and train the model by implementing all these components. Then only we should apply that particular and training to the model, whether we will be giving zero short learnings or few short learnings, and make the model as accurate as possible. Especially in medical domain, we need to minimize errors so that it will impact the real world. I think I hope I answered your question. So that's a good question. We should take care of using all these techniques. Yeah.
Good evening, madam. Good evening, madam.
Yeah, yeah.
Hello. Good evening.
Yeah, good evening.
I'm Professor Rajkumar from JNN Institute of Engineering. I have one question, madam. You
Yeah.
are given that unstructured text data from the feedback form. Suppose I'll be having which method I'll be using? Either I'll be a bot or I'll be having the GPT. How will you make it as a training for this example?
How we can?
Using this, which one we can using for this, madam? Bot or we can have the GPT? If it is unstructured, we can go for a pre-processing. That pre-processing we can have some training model must be there. That which one is the best? Be a bot or we can having the GPT. We can have a different GPT is there.
Yeah.
Which one is up for this?
Okay, this is also a very interesting question. So if you see here, if you take earlier GPT models, the main limitation of that is token limit. So
okay, yes.
Yeah, so that's why if we have like large unstructured documents, okay, that's why here if we use GPT-2 kind of models, the token limit is very, very limited. But if you see now GPT-4 and advanced versions of the LLM models, they have much, and also if you see Gemini Pro, that has millions of tokens.
Yes, yes, madam.
Yeah, Gemini kind of models can analyze our text in a much better way. But the problem here is, like, if we want to take some like millions of transactions, then that will be difficult. But what I suggest is for solving this problem, instead of talking about LLMs, I think you people heard about this Lang chain or RAG framework.
Yes, yes, madam.
Yes.
I'll be using the long chain, madam.
Yeah, LangChain is nothing but no. If it will make the, like, if we see the pipeline will make the process simple end to end. But for solving this problem, RAG is good. RAG is nothing but here we can store that unstructured data using vector DBs. So vector DBs are nothing but if you see earlier we used to have this relational database management systems, right? Like that, if we have large number of unstructured documents like that, we need to store them in a efficient manner. Efficient in the sense there should be some good indexing mechanism. So I want to, I have some Oxford dictionary. Let us suppose it. I want to, like, how I can go to the specific word, and because I have a good indexing mechanism. Likewise, same problem we can solve by storing this textual information or documents in vector DBs. So we can try like Pinecone and Milvis, Chroma. These are all many different vector DBs, but I suggest you to store this in a vector DB like Milvis. Then you convert that into embedding models like advanced embedding models. Then you can use Gemini kind of models to process or get some insights where it has or otherwise you can use Llama or Falcon models. These are all open source LLM models, and get the information. But I don't suggest to use earlier transformer, like earlier GPT models like GPT-2 or GPT Turbo like that. So this is the mechanism generally we will be using to solve this use case. I hope I answered your question, right?
Yes, madam. I understand.
Yeah. Okay.
Thank you, madam.
Yeah.
Rajkumar sir, can you please switch on your video, please?
1 minute.
Yeah, I think I have some more content. Sorry, I can take the questions at the end. Is it fine, Ramabu sir, because I have some more content to present?
Okay,
Yes,
madam.
that's
Carry on,
fine.
madam. You carry on, madam.
Because I want to give that inputs also. It will help them actually. So to give some of the code snippets. So how the audience are asking related to GPT, like that. What problems actually we can solve using that? I want to explain that. Then I will take the questions further. Okay.
I continue, madam. Thank you.
Yeah, and also I have some MCQs. So Rambabu sir, they can post the answers in the chat. You please verify because I am presenting here. I want you to take the answers. So this is a simple just to whether like I want to engage the participants. So this is like totally we have only 4 MCQs, not much. I want you to verify the answers.
Okay, madam. Thank you.
What is the purpose of tokenization NLP? So everyone, so because I'm not able to see the chart, Ramab sir, actually is in presentation mode. You please let me know how many are able to answer these 2 questions. In the chat, I have more responses.
Okay, ma'am.
Yeah. So we will give like 2 to 3 minutes time here and jump on to the next topic, LLMs.
One is that is identifying the emotional tone text.
Yeah, you please know as audience are like good enough number. I want you to post your answers in the chat so that Rambabu sir will later verify that. Okay. Once done, please let me know, sir. I will navigate to the next slide. Sir, you are able to see the answers in the chat?
Yes, madam.
Yeah. So once done, but at least if you are able to touch 50, then I will navigate to the next slide.
Okay, madam.
Please let me know, sir.
Okay, madam. Okay, madam. Go to next slide, madam.
Sure. And also I want to give like these are straightforward questions also only, but I will give the answers at the end. So I want to spend half an hour more in LLMs. Sir, once let me know once you get the answers.
Okay. Okay, when I continue, madam.
Yeah.
Over.
So, okay. Now,
Thank
I
you.
think, yeah. Thank you, sir. Then I think we have spent enough time related to NLP. So let's transition to LLMs. So if you see, NLP techniques are effective, but the thing is, they are rely mostly on the rules and also the context limit. Only if we use NLP, the earlier techniques. But if we use LLMs, they will overcome the limitations because as we have seen the transformer architecture and also the kind of training that is given to the LLM models, they are highly contextual, and also they can like if you see advanced GPT kind of models and other open source LLM models, they can understand the text and also they can give the responses instantly. And what are the various tasks that LLMs can do related to the healthcare domain, we can go in detail. And actually, what exactly is LLMs? So I think you know the enough background related LLMs, but let us spend a half minute to 1 minute in this. So this the basic for LLMs is neural networks. So they are advanced neural networks, and they are designed, they are trained and large corpus on massive data sets, and they excel in tasks requiring question answering mechanisms, as I narrated, and also we can summarize the content. So as we discussed just now, so how they are able to use this lang chain and advanced RAG mechanisms and able to make the task very simple. And we will see like as the concepts like LLMs are built on the transformer architectures. So that's why they are like how they are able to capture the context and how they are able to generate human-like responses and understand the text. So they are wholly based on self-attention mechanism. So it is not, I'm not explaining about architectural diagrams on a high level, what are the core concepts, because the other things are already covered. So if you see, self-attention is nothing but it helps the model focus on the relevant parts of the input. So if you remember the earlier session ma'am has taken, so she has given the like enough narration on the self-attention mechanism and also the positional encoding. So how these architectures are able to maintain the sequential order of words. So that is also explained. And if you see, just now we had a question, very interesting questions on many whether there is a spell mistake or whether we want to train unstructured documents. So what are the models that we prefer and what are the architectures? So GPT is nothing but generative pre-trained transformer. They excel in text generation, but if we use BERT, it is a bidirectional encoder representation from transformers, that is a full form, and it is designed for understanding the context of words in both directions. So the BERT acronym itself tells us that. And this is also very important nowadays. Private LLMs has become very popular. Using advanced RAG mechanisms. So pre-training is nothing but LLMs are trained on a large corpus of information to learn the general language patterns. Whereas fine-tuning, we need to pre-train the models to specific tasks. Like I want to, if you see medical records or any confidential information, I want my own private LLMs and I want domain-specific information to be trained. So that is nothing but fine-tuning. So here also like tokenization, these all things are already explained by me. So yes, just now we will see like if we take some advanced models there, we need to have like infrastructure and also we need to have a lot of GPUs. But from Hugging Face, we can have some downloadable models using Collab also, and we can work. We can I want to narrate a code snippet. So here I have used only GPT-2, and also the limitation, as I told, the token limit is a main limitation. So here I have given input prompt like advanced in NLP have significantly improved. So I am asking to complete that particular sentence. So here it is a generated text. It is able to give the, like, as it is simple text, and the maximum length also have kept only 50. So here it is a straightforward example just to narrate the flow of the like LLM models. And what are the like here we want to spend some time because what are the healthcare challenges actually LLMs can address. At the end of the presentation, I will also be explaining what are the limitations, because LLMs also suffers from few limitations. So what are that also we will discuss. But for time being, question answering mechanism is like very popular, and nowadays many people are working on this problem. So we want to know like some complex questions about some symptoms or medications. We can develop some powerful medical question answering mechanisms, and also we can get some contextual answers. So that is very important use case. And also doctors, they like in terms of summarization, already we discussed a lot about summarization. Like that, if the doctor wants to, no, it will not have that much time to go through the entire patient record. But if we are able to give some summarized, like good information to him, then that will definitely help the time and get the glimpse of information. And also we can predict the drugs, like drug interaction prediction. We can use what are the potential interactions by using few short learnings. And we can highlight the potential interactions from the medical notes. So we can, like, prediction is also another important use case. And also if you see healthcare chatbot, so nowadays in many hospitals we are not only nowadays, earlier also, but now the mechanism has changed. They are able to get the support around the clock with accurate responses. But earlier the responses are not that much accurate. But now, because of the the training that we are giving, and also the kind of mechanism and the framework that we are using, and because they are learned on corpus, huge corpus, they are able to handle the textual information and able to give the apt responses. So these are some of the problems that we can solve using LLMs. So just here, I want to explain a code snippet. I'm not going to the complex LLM models, which require much context and much tokens. So here I have taken only a context, like John, it's the same thing. Like a 45-year-old male visited the hospital with symptoms, and this is the textual information context I have taken. So what I am making the LLM model to is, here I have used Distilbert uncased. So we have many models. You can just test with any of the other models as well. So just for illustration that in a question answering mechanisms, here I have used GPT, but as I told, we have many advanced LLM models and open source LLM models where we can use them, and we can scale the data, and we can use advanced RAG mechanisms also, and get the question answering mechanisms done. So here I am asking a simple question like, what symptoms did patient experience? So what LLM is able to read that particular context, and in this simple example, it is able to answer. So what is the particular symptom did the patient experience? So likewise, this is just a very, very, very simple example. Likewise, we can have n number of textual documents, and we can give prompts and load that particular textual documents using vector DBs. And later on, we can create that, but we can convert that. We can do enough number of pre-processing, and later on, we can convert them into vectors, that is embedding models, using embedding models, and we can store them in a efficient vector DBs. And later on, using LLM models, we can retrieve the answers. So that's how we can build effective question answering mechanisms. And if you see here, so coming back to our story, what exactly like LLMs can do in this John's journey. So diagnostic insights. So LLMs could generate explanations for John's symptoms. Like it can link to likely causes also, but definitely there are some limitations that also we will see after this. And treatment suggestions. It can offer some personalized care plans based on the context. And it can the continuous learning over time. It can integrate the latest medical research because it will be trained like I don't know like exactly latest ChatGPT is trained on. But it will be trained on the latest medical research and accordingly it can answer. So that is how the relevancy of LLMs in John's journey. And yeah, now again, I want to have 5 minutes discussion. So in this, I want like how can NLP improve patient-doctor communication? So it's time for anyone to answer this question. So we have spent some time on LLMs and how exactly they like what kind of problems we can solve using LLM models. Now I want you to speak. So this is one discussion point. How can NLP improve patient-doctor communication? So just a brush up of the NLP that we discussed. Anyone? Otherwise, I have like other discussion points. So I want like this is I think this is very interesting discussion topic. You can share your thoughts. Can LLMs replace like it is a kind of debate? Can LLMs replace medical experts? I want you to unmute yourself and share your thoughts. Anyone? And I need a justification why or why not. Rambabu sir?
Madam.
Yeah, I think this point is debatable. I want the participants to answer this.
Okay,
And
okay, madam.
express their thoughts.
Participants, you can unmute yourself and you can ask. You can say.
Yeah, that is nothing wrong. We can express no
Okay,
we can give justification or what do you think? Otherwise, Rambabu sir can answer this. So, like, what is your opinion related to can LLMs can do that or not?
Madam, lot of participants given that message, madam. Please check once.
Okay. No, as I told you, I'm not. Sir, can you help me to read the answer because I'm in presentation mode. I am not able to see the responses.
Ma'am,
Yeah.
this is Dr. Chandrasekhar.
Yes, sir.
State of mind. That is, he depressed or having more anxiety.
Yeah.
At that moment,
Yeah.
he will tell what actual problem. Without actual problem,
Yeah.
he will tell other things like, so I am pain, I am getting pain on left side because of not having proper sleep.
Yes,
because of
correct.
some other psychological problems.
Correct.
He may not give the proper text for that.
Correct.
So for that, how the LLM gives the solution for that problem?
Sir, actually, so that's why this is a debating topic and your question is no practical. So here LLM can go with the data, right? So here if we see the kind of, we need to see the based on the tone. So we have speech to text mechanisms. So based on if there is a lot of research going on, whenever the patient is speaking, so whether if he is confident, and we will be conducting many psychometric tests, right?
Yeah.
We need to understand the pattern. In that case, this is a very medical research. One of the problem, like I don't remember the universities or in which foreign university that is taking place. But what you are asking is, so there, if whatever the patient is saying, if we directly convert that into text and if we make the LLM model to answer, that won't help here, because he may not be in a state to explain in what situation he is at that time. Like based on the movements or the based on the gestures or based on the emotions and the kind of frequency, like that the like text, like speech to text kind of psychometric tests are needed, where like based on the level or the frequency of that particular words, we need to detect that wave. And yes, based on that only. And I have seen like in one industry also, they are doing this, they are solving this problem in that way. So they are going to the n number of patients, and whenever they come to the doctor suddenly, they need to capture whether they are saying the right information or not, and what is their past medical history. So at the time they won't be giving the right information. So that's I'm telling. So we need to have extra information to give the model, learn the correct information. So we can't rely only on the textual information and go ahead with the answer. So that's why I'm telling that.
The supporting information is required for analysis.
Yes, that is required.
Yes.
So otherwise, LLMs can't alone be like medical experts.
Yes,
so that is one of the interesting research,
Yes,
and good you have kept here before the many people.
Thank you, ma'am.
Yeah.
Ma'am, one more thing.
Yes, ma'am.
We cannot expect patient to know about the medical terminology. Only LLMs can be trained on the medical terminology only. Then how that is NLP can be able to replace that medical experts? It is not possible. Why? Because here LLMs only based on the medical terminology only, not on the common language.
Yeah.
So all patients, we cannot expect all the patients come to know everything about the medical terminology, as well as they know they all are computer experts or computer illiterates.
Yeah.
Computer illiterates also may be possible. So then we cannot expect that is LLM replace the medical experts. So up to some extent, what some extent, at least 30% or 20%, that is only possible, but 100% is not possible.
Yeah, good. I'm
Ma'am, one more thing.
responses.
Ma'am, one minute. Recently, 2 days back, I read that Elon Musk's tweet.
Yeah.
That is mentioned like that AI will soon be doctors also.
Okay.
So how it is possible that LLMs is going for their area?
I think no. I told LLMs no. If we take this topic, this is a very exhaustive, debatable topic. It can't replace the medical experts for sure. A manual intervention is needed. Okay. Because we have some models like BioBert and some other medical related trained models, but as one of the participants just now told, so they can't give the medical terminology directly, so they will say in a layman language only. Okay, we need to give some training to the model in such a way that it can learn the medical terms, and based on that it can learn the symptoms accordingly, it can act. But like to the up to today, I think like LLMs can't replace this medical experts, but we will see how the technology will change or evolve. Yeah, we will go ahead and with the other discussion topic. So how do you think summarizing patient records could benefit hospital workflows? So you can take at any point, so from when we go to the hospital until the end. So in what case this it can summarizing can help in the hospital workflow? Any one answer?
Madam, yes, actually summarizing is that is good. Why? Because summarizing the patient records, in order to analyze all the records, if a number of records are there relating to one patient.
Yeah.
Summarizing all, verifying all the records is not possible in short time. So if we use this our LLM or NLP, then it is very easy. What exactly it is required summarization or summarizing that all the record data. By that, then hospitals, that is a doctor will take the decision to how to treat the patient.
Yes.
That is very good.
Yeah. Okay, these are some of the things. And also what precautions, yeah, this is also very important and debatable topic, and everyone should know. So what precautions should be taken when using LLMs in healthcare? So this is well known to all, but anyone can answer this. So what is the challenge or limitation when we use LLMs in healthcare? So now,
Ma'am, we can serve
yeah.
we can serve as a biologically back step for intelligence.
Okay. So other than that, so I'm expecting some more. Like one very challenge thing is there when related to healthcare only. So
Whether it is biased or not, I mean, the information that is fed into the LLM is, I mean, we need to check our
correct.
whether
Yeah.
biased information.
That is related to not only biased. The one thing challenge is like many hospitals, the challenge here is the patient's information is very confidential, like private, right? We should not use it as it is. So the data privacy is the biggest challenge here when we use this open source kind of LLM models. So we should take utmost care, like which data has to be trained, and because data privacy is the like basic challenge here. Yeah. And I think we have discussed and a lot of brainstorming is done. So let us conclude this, and I have some other things to discuss. I will quickly close that as well. So what are the key takeaways from this 1 hour session is NLP and LLMs are they can be used in healthcare for unstructured data pre-processing and also decision making. And also we have some future directions like related to bias, and as I told, data privacy is a major concern. And as I told, like one of the very interesting question I got, whenever the patient is not in a position to explain in in that case how we are able to handle that, we need to integrate with wearable devices for real-time symptom monitoring. So as I discussed, these all things has to be done. And also we need to no, and also multilingual capability. That is also very important. So we need to expand the LLMs not only in one language, and also multilingual patient records has to be captured. So these are some of the future directions. And also I have some other things to present. Let me navigate to that slide as well. Yeah. One thing is, so discussion topic answers, I want to give it to you at the end now itself. You can see what are the answers that I have given here. So first discussion topic I have given is how can NER transform patient record analysis in hospitals, sorry. So we can identify the key symptoms and we can extract the medications as well as disease names. You please check, like these are some of my thoughts. Likewise, what approach would you take to analyze unstructured text data from patient feedback forms? So this one, like one faculty member, I remember, she is able to explain the same flow, tokenizing and also text classification and visualizing these all things. And coming to the answers, I didn't verify it, but at the end of this session, I will verify. So these are the answers for these 4 questions. I think I didn't give this. And I like at the end, like I have 5 more minutes left. So I want to present this, what are the problems and also what are the limitations, and some case studies as well. So let me zoom this. So what are the problems related to what are the limitations of using NLP and some case studies. So first, a case study that is already used or already developed is, if you see clinical note summarization, we have spent some time on summarization. So here, if we see healthcare providers, they will be facing challenges in managing large volumes of unstructured patient records. So in this case, we can use any NLP or LLM based approach like bird based summarization. So here, using that, they are able to reduce the time spent by doctors. I think these are the real case studies already. They are in place. They're able to reduce the time spent by doctors in reviewing the notes by at least 60%, so that they can allow more time for patient care. So that is live and production. And also, if you see, another problem is symptom analysis from chart logs. So we can, as I told, we can, the problem here is difficulty in identifying the key symptoms in patient-doctor chart interactions. So this also we have discussed now. So how we are able to overcome that, and some of the future directions I have given. In this case, we can use NER kind of thing, and we can extract the critical entities or symptoms and medications, so that using NER, we can improve the accuracy of telemedicine services, leading to faster and accurate patient referrals. We can do that, as well as another problem is detecting the potential harmful interactions between the prescribed medications. So this is also related to drug interaction warnings. So they have used, like, BioBert is one LLM model related to the medical domain. So BioBert is used for solving this problem, and they are able to know 90% accurate prediction of risky drug combinations. So they are able to do this. And this is also one very interesting use case in terms of new fake news detection, especially in COVID time. We have we got many fake news articles related to whether the COVID vaccine got approved or not approved, and related to the treatments as well. So here, some in one of the research papers, they are able to use LSTM. LSTM is explained by the earlier speaker well, so related to how the like sequence to sequence modeling, how it is happened. So using LSTMs, they are able to identify and flag the fake news articles based on the textual patterns. So using that LSTM kind of models, they are able to identify like 95% accurate detection of fake medical news. So, like, not only LSTM kind of models, we can try other approaches also. But this approach is tried, and they are able to improve the, like, they are able to detect the fake news articles accurately. And other thing is, like, I want to know the hospital resource allocation. So here, the problem statement is how we can predict and manage the peak ICU demand during emergencies. So how we can do this problem. So just we are giving here the kind of no approaches used in literature, but each of you can take some of these problems, and you can solve in your own way. So here they are used transformer-based time series modeling, and using that, they are able to predict the resource usage trends for optimal allocation during the demand. So using this approach, they are able to optimize the ICU resource allocation, and also they are able to reduce the shortages and improve the patient outcomes. Yeah. So with, like, these are some of the challenges or the problems that are already solved in the literature, and also some of the approaches. But each of you, based on the the POC, or if you want to develop your own solution, you can go ahead with your own solutions. And finally, I want to conclude. I have 1 more minute left. I want to conclude this with no limitations. So actually, we have discussed a lot about LLMs and NLP, but the main limitation of LLMs, or some of the things, is data privacy concerns. This I already discussed, and bias in the models. So main problem is hallucinations. They are trained on biased data sets, and they may produce unfair or inaccurate results. So that is one issue. And many small industries or mid-level industries and other people, what they are facing is high computational costs. They need a lot of GPUs to train and deploy the models. So a lot of computational resources are needed. So that's why to deploy the models, we want to have Azure servers and some other cloud platforms, and GPU enabled systems. So these are a little bit no complex because of high computational costs and lack of explainability. So explainable AI is in place. but we need to integrate that. And like LLMs are giving answers, but we can see as black boxes, because sometimes it is difficult to understand how they are able to make the predictions, especially if we see the criticality in healthcare. So these kind of problems, they are giving the answers, but it is difficult, very difficult to come how they are able to come up with that particular prediction. And also, if you see, they have like LLMs are trained on generic data, large corpus on the open domain, but they can process large amounts of it, but they lack the understanding of healthcare professionals. So that's why now people are developing private LLMs and training their own in-house data. And also overfitting is also another issue. And another thing is ethical and legal challenges. So misuse of LLMs or inaccurate predictions can lead to the legal consequences. So these are some of the limitations or challenges of the LLM models. So some of the way forward techniques, or some of the problems that we can work with is, so how we can integrate with the domain expertise, so based on the overcoming the limitations. And also we have already some models like healthcare problems we want to solve. We have already healthcare related models like BioBert, Clinical Bird. They are exclusively trained on medical data sets. And also we want to make our interpretation much more simpler. We want to improve the explainability of the models, and enhancing the data privacy. So because data privacy is a concern, and we need to reduce the bias in terms of training the models on diverse data sets, and monitor for biases. And also collaboration across disciplines. We need to do that, a lot of collaboration with AI researchers, healthcare providers on a and we can address this collaboratively. And also we know we need to work on, like nowadays I think people are already in place this quantized models like LoRa and QLoRa. These are quantized models. So instead of representing the entire model like in a 32-bit, we are reducing that into quantized bits, that is binary quantization and scalar quantization. These techniques that we are using, and making the resources like LLM architectures more optimized. So that's how we are able to optimize the models. And yeah, I think yeah, before we end, I have one more, like these are some of the tools or frameworks that we can use. So as part of the tokenization, already I have given enough number of like code snippets. We can use Spacey, NLTK, and Hugging Face. And text vectorization, we can use TF-IDF model, and as well as GenSim and scikit-learn. And for NER also we can use Spacey. And text summarization, we can use T5 transformer model and BirdSum. As part of the question answering, we can use Hugging Face models, like LLM models from Hugging Face. And also by using OpenAI keys, we can access that. And if we want to do text classification, we have many models. Just I'm giving some examples. And also if we want to do embeddings for healthcare, we can use BioBert and as well as Clinical Bird. And for doing graph analytics, we have tools like Neo4j and NetworkX package, where we can model the relationships between drugs and symptoms. So we can, like I have given enough a description of each of the categories. Likewise, these are some of the references, like for the BERT, we have like BERT paper, and BioBERT, we have the base paper. And transformer based models in biomedical, like these are some of the references where you can refer. And a lot of open source articles related to the evolution of LLMs, and also a lot of research related to NLP is also done. I think I am good from my end, and I think I have covered related to what are the healthcare challenges, and how NLP, and in what scenarios we can use NLP, and in what scenarios we can use LLMs, and what are the limitations, and with enough number of theory as well as some core snippets. So I think I am done from my end. Yeah, thank you for this opportunity. I think like some insights might be useful to you, and I encourage all of you to solve some of the use cases, and actually test with n number of models or n number of experiments, how each of the approach is working, and how actually in what ways this technology is solving your use cases. Yeah, over to you, Anush. Over to
Thank you, ma'am. Thank you, ma'am. Now I request that all the participants, please, can you please switch on your cameras? We'll take one photograph, please. Meanwhile, if anyone wants to give any feedback, please, you can switch on your cameras and you can give.
This session is more interactive, and Madam has explained very well. And whatever the content is, Madam has displayed and explained. That is very well organized. Thank you, Madam.
Thank you, Narendra.
Good evening,
Anyone?
madam. Good evening, madam. Very nice presentation. Very nice presentation, and then explanation depending on the queries from the audience. It should be very good, madam. Thank you, madam. Your presentation is very clear and then audible, madam.
Thank you,
madam.
So, Rambabu said done.
Just wait, madam. Just wait.
Hello, ma'am.
Yeah, I'm able to hear you.
Okay, madam.
Thank you. On behalf of our entire organization team, I thank Dr. V. Sirisha ma'am for gracing us with her presence today. Your valuable insights and time have made a significant contribution to this event, ma'am. Thank you so much, ma'am.
Yep. Yeah, Anushka, it's our pleasure, and thank you. And I hope this session can be used by all the participants. Yeah, have a great day. Yeah.
Sirisha, madam. Thank you, madam.
Yeah, thank you, Rambabu sir. Yeah,
Thank you,
nice interacting with you, all of you.
Yes,
Actually, a lot of brainstorming and good questions from the participants. It's nice interacting with all of you.
Very good interaction.
Thank you very much, madam.
Yeah. We'll share that feedback form in WhatsApp group. Please kindly fill that form.
Okay, ma'am.
Thank you, ma'am. Thank you, sir.
Yeah, is it fine? I can exit from the session?
Yes, ma'am. Thank you, ma'am.
Yeah.
Have a nice day, ma'am. Thank you. Good night.
Same to you, good night.
Thank you all. Tomorrow we'll meet you at same time, please. Thank you.
Thank you, madam. Thank you.